we are continuing to find the volume of solids or revolution, but we're going to switch to a new method called the cylindrical shell method. So previously we've done discs and washers, so let me talk to you about why we would bother with this. We're going to spin this around the y-axis. So if I took this region, right? So to try to visualize it, that's pretty bad. We try to reflect it. And we understand that this would be a three-dimensional solid. This would be kind of like a bundt cake, right? Like this is solid all the way around. Now, if we did the discs and washers, we would run into a problem, because if we drew it, right? If we drew one, notice how the same curve is both the outer and the inner radius. So when I do the outer radius minus the inner radius, I would get 0. And the volume of this solid is not 0. That is like a huge problem. Some curves you can kind of handle that through symmetry, but this one would give us trouble there. So we need another way. And basically when you're finding these volumes of solids, you're chopping it up into small pieces. When I did the washers, you could imagine taking slices like this, perpendicular to the axis. Another way to do it would be, suppose you had an apple, and you had an apple peeler, where you peeled the outer layer, and then the next layer, or a potato if you prefer, and you just keep peeling it one layer at a time until you just get in and in towards the center until there'd be nothing left, right? You're shaving it off one peel at a time. That is precisely what we're doing. Instead of like just being trashed potato shavings, imagine that you could go around and keep it, that circle, that whole peel around the outer edge, and you could just take it and keep it. And then do the next peel all the way around, and it stays a complete whole circle, and you could take that off and keep it. What would form is a whole bunch of this is one representative shell. Right? Imagine I had the peeler and I go around and I peel one layer off. It's really thin, right? And I could just lift that out. I'm not sure if you're seeing it. There is a video I'm going to include as a separate link that kind of shows you this. So you can at least see one of these shells moving through the object. But this is what we're getting at. So basically, I would have a whole bunch, and there'd be another one right next to it. And there'd be another one right next to that. And I could do this for the whole solid. So if I could find the volume of the purple shell and add it to the volume of the red shell and add it to the volume of the green shell and add it and add it and add it, if I added them all up, an infinite sum, an integral, that would give me the whole volume of the whole solid, right? So let me just pause here and show you this. So this is a cylindrical thermos, right? I'm not talking about a cylinder that is solid. I am talking about a cylindrical shell, right? This is a cylinder. It is solid. This is a cylindrical shell. It is empty on the inside. This still has a volume, right? This has much less. The volume of this cylinder would be it and all the space inside. The volume of this shell is literally just the volume of this piece of paper. That's what it is, a piece of paper taped, right? So it does have a certain volume, but I'm not talking about all the volume inside of here. I'm talking about just the volume of this sheet of paper. Now let's look at that for a minute. Here's a sheet of paper, and here's that, let's say I put a mark right here. Let's make this the end. So I'm going to take this, and I'm going to take this end of the paper, and I'm going to curl it around and make a shell. Well, let's start with the paper. What would the volume of this piece of paper be? Well, the volume would be the length times the width, or let's call it the height, the way I've drawn it, times the thickness. So that would be L times H times T. Okay? Well, now look what happened here. Ugh, what did I just do with my red marker? So look what, I bent that around. This is still the height. But now look at the length. That is now a circle. 2 pi r is the distance around that. See, the length is 2 pi, that is the circumference of that circle. That length is that circumference, 2 pi r. And the thickness of this is going to be very thin. Remember in calculus how we think about this is the thickness, this is a smaller thickness. What is an infinitesimal thickness? I would call that, let's call it dt for d thickness. So the volume of this would be 2 pi r times h times the thickness, which is infinitesimal. 2 pi r, right? So this is length, width, and height. So I get this equation, but this would be the volume of just this one piece of paper, just this purple piece of paper. I would have to add that, so I'd have to add the purple 2 pi r dt. I can't find my red marker. I would have to add that to the red 2 pi r h dt. And I would have to add that to the green. And this radius would be a little bit bigger than that radius. So let's call this radius 1. Let's call this radius 2. Let's call this radius 3. See that radius is changing. It's growing. The height is always the same there. Well, the height is changing, but, well, the height is changing. So we'd have height 1, height 3, height 2. The thickness is always infinitesimal, so that stays the same. So if this is the volume of one sheet of paper or one shell, this is the volume of one shell. In calculus, how do I add up an infinite number of these things? It would be the integral, the infinite sum of all the 2 pi, and now I understand this r is actually variable. This r is in a state of changing, times h, which is in a state of changing, times the thickness, right? So I'm going to just alter this. So I'm going to write, this would be 2 pi times the radius times the height times the thickness. And that thickness is always going to be dy or dx. All right, that is hugely important. That is so important, I'm going to erase everything else, and I'm going to take this because this is our main equation. All right. So volume, now 2 pi is a constant, so I'm going to pull that outside of the integral. This will be radius times height times thickness, which will always be a dx or dy for us, right? Now I'm going to call this a conceptual equation. In your book, you'll find two versions of this. A lot of times you'll see this, right, for x and y. You got to be careful with that because this is only true if you're revolving it around the x or y axis. If you do it off offset, you have to adjust this. But we won't worry about that for now. This is the key. This is the key. This see how that flows? Now, this you got to be careful. You can't see that very well. Not a good time for my markers to go. All right, so we got to be careful. Well, that's kind of the lead in, that's the logic. Okay, so how would I do an actual problem? So I'm going to erase this, and we're going to do our first problem. This is going to be pretty standard. So let's try this one first. Find volume of solid generated by rotating the region defined by those three boundaries about the y-axis. All right, so it took a lot of words to set up the question, but here it is. And I'm going to need my calculator at some point. All right, so the first thing we do is we draw a picture. So this is the cube function, a variant. Y equals 0 is this x-axis, and x equals 3 would be right about here, right? So I'm going to draw a prettier version of that. I know this is at 3, this is 0, this is the x-axis, this is the y-axis. I'm pretty sure I'm going to be interested in that point. That is where 1/2 x cubed, that's where x equals 3, right? So that point, maybe that's what we want. That point would be 3 comma 1/2 times 27, 13.5, right? So that's that point. I'm pretty sure we're going to want to know that. All right, what are we supposed to do with that? We are supposed to rotate it about the y-axis. So let's do that. Imagine that this is this solid, right? Now, I'm going to try to take the volume. I actually could do this with washers. It wouldn't be a problem, but I want to learn how to do this with shells. So what I'm going to do, see the axis of rotation? Instead of cutting it perpendicular, I go parallel to the axis of rotation. And that's going to spin around and create a shell, a cylindrical shell. And that shell has a certain radius. Notice the radius stops when it hits this function. It's got a certain height. Notice that stops when it hits that function. And it's got a certain thickness. Now, the thickness of this, if I was going to measure how thick this piece of paper was, I would have to put my ruler like this along the x-axis to measure how thick that was. That's how I think of it, like, so I never got to guess. This is a dx thickness because I would measure its thickness by putting the ruler along the x-axis, right? So that tells me I'm going to need a dx integral. So this is going to be 2 pi times the radius times the height times the thickness. All right, so what is the radius of the shell? Well, it goes from here out to here. That is x units. Right? See, r is x units. And h is y units. So I can use x. The radius is x, but I cannot put y because this is a dx integral. It's x units over, it's y units up. Well, it's y units on that curve. So this is my height, right? See, this is why the height is the function, right? The height is going to be the function. That's how high it is. 1/2, let me write that in purple. 1/2 x cubed. Well, that felt pretty stilted. We've just done the hard part, right? The rest is all easy from here. If you can get this equation, all we need is our limits of integration. So let's see here. Here's the region in question. Here's the original region. This x value will be where the x's started, 0 of the original region, to where the x's end in the original region. So there's my integral. I could tidy this up a little bit. I could pull this out. And I could do this in a calculator, but this doesn't look that hard to do it by hand. So this would be pi times 1/5 x to the 5 from 0 to 3 dx. So I'm looking at pi over 5 times 3 to the 5th, which I think is 243, minus pi over 5 times 0. So 243 pi over 5 units cubed. Right? Volume equals, volume equals, volume equals, volume equals. So if I just walk back through this, I get my original region, bonk, rotate about the y-axis, that gives me the purple. I'm doing cylindrical shells, so I'm going to do a slice parallel to the axis of rotation, and that forms a cylindrical shell. There's the radius, x units out. Here's the height, y units out, but I can't use y, so I use the function. So the height is 1/2 x cubed. The thickness is dx, and the rest is old school. Let's try another equation and go about the x-axis, and we'll call that good for our first lesson. So I'm going to erase this, and all of this. All right, problem number 2. Step 1, try to find the original bounded region. That's this one. That's this one. And that's that one. So here it is. I'm going to recopy that and make it look pretty. Or maybe I should say prettier. So there's that region here. And now I'm going to revolve it around the x-axis. So I'll reflect this, swing back up there. And I'm going to try to do this with shells. So I got to cut parallel to the axis of rotation to see my first shell. This is a dy thickness because the thickness of this shell, that would be measuring how thick the paper is between my finger and thumb right there. I would hold my ruler up like this, that's parallel sits dy in the y direction. This is a dy thickness. Here is the height, and here is the radius. Notice that the radius is exactly y units up, and that's fine because that's a dy integral. My height, however, is between the two curves. Between the two curves. So my height, and you always go high minus low, big minus small. So that'd be right minus left. So this would be my height. However, notice, see how it's in x's? I can't have that. This has to be all y stuff. So look, see how y equals x? Right here. There's that one. And then this one, I got to do a little side work. So this is that function solved for y. This is the same function solved for the other variable. So this is the height I need to use. The radius is going to be y, and my thickness is dy. I think we're pretty much good to go, so let's set up our equation. So for shells, the volume is 2 pi times the integral of the radius times the height times the thickness. And the original region begins at a y value of 0 and ends right there. So I have to figure out how high that is for right here. So what I'll do is I figure, well, that would be where this intersects with this. So we're looking at y equals 2. We want the positive one, not the negative one. So this would be at y equals 2. So right there is my raw integral. If I can find out what that is, I have my numeric answer, right? We're going to tidy it up a little bit first. I'm going to leave that there for you. So this would be 2 pi times the integral 0 to 2 of y squared minus y cubed plus 2y dy. And we could do that by hand or by in the calculator. I guess I'll punch this one in the calculator. It'll take me a minute. Sorry about that. So I got almost there. From 0 to 2. So my calculator is saying 16.76 units cubed. All right, so we'll let it be there. You're going to need to try a few of these problems, setting them up, and we'll kind of see where we're at after you try some.